Welcome to the first how-to tutorial for CHM1011. This is the first of about 20 video tutorials that we've designed to assist with the first 5 weeks of the unit. The first tutorial talks about interconverting between wavelength and frequency, specifically with respect to electromagnetic radiation. It's important to understand a bit about electromagnetic radiation if we're to understand about matter, atoms, atomic structure, molecules and molecular structure. It's through the interaction of radiation and matter that we actually know so much about atoms and molecules. To understand the electronic structure of atoms, one must understand the nature of this radiation. In the waveform below, a couple of things are defined: the wavelength and the amplitude. The wavelength, which is often indicated using the Greek letter lambda, can be seen here. In this case, it's defined from what we say is peak to peak. You can measure it from trough to trough, or from two equivalent points anywhere on the waveform. It's always going to be the same. This is the wavelength. This displacement here, as indicated, is the amplitude. The number of waves passing through any given point per unit of time is called the frequency, and it's often indicated using this Greek letter nu. Notice this is not the letter V, it's actually a Greek letter. For waves travelling at the same velocity, the longer the wavelength, the smaller the frequency. In these two examples here, this wave has a shorter wavelength than this wave here. So this wavelength has a higher frequency. All electromagnetic radiation travels at the same velocity. The speed of light, often indicated by the letter C, in a vacuum is 3 times 10 to the power of 8 meters per second. And the relationship relating frequency and wavelength is nu times lambda equals C. The electromagnetic spectrum that you see in the figure indicates that the visible region, the region that our eyeballs detect, is actually only a very small portion of the electromagnetic spectrum. At the long wavelengths we have radio frequencies, and at the short wavelengths we have gamma rays. Now, for a problem where we interconvert between lambda and nu, between the wavelength and the frequency. A dental hygienist uses X-rays, lambda equals 1 Armstrong, to take a series of dental radiographs while the patient listens to a radio station, frequency equals 105.1 megahertz, and looks out the window at the blue sky, lambda equals 473 nanometer. The question: interconvert between frequency and wavelength in each case. Assume that the radiation travels at the speed of light, 3 times 10 to the power of 8 meters per second. Let's go through these one at a time. In the first question, we're given a wavelength, 1 angstrom. Firstly, we have to change to SI units, and the units for length, meters. So the first step that we do here is convert the wavelength to meters. You may not have heard of an angstrom before. An angstrom is 1 times 10 to the power of minus 10 meters. So to interconvert, we multiply by this factor, and we get the wavelength in meters. The question is asking us to convert this to a frequency. We rearrange the wave equation so that nu equals C divided by lambda, the speed of light divided by the wavelength. C is constant. Three times 10 to the power of 8 meters per second. In the previous part, we converted the wavelength to meters. Plug this number into your calculator, and you should get something that looks like this, seconds to the -1. Frequency can be expressed as seconds to the -1, or it can also be expressed as hertz. In the second part of the question, we're actually given a frequency. First thing we have to do is convert this frequency to SI units. So that's either seconds to the -1 or hertz. Our frequency has actually been given in megahertz. To convert from megahertz to hertz, we multiply by this factor. There are 1,000,000 hertz in a megahertz, okay, or 1 times 10 to the power of 6. In which case, plug that into your calculator and you should get a number which looks something like this. The next step, we need to convert the frequency to the wavelength. Oops, and as you can see, I've done it incorrectly. Let's try that again. We want to calculate the wavelength. Speed of light divided by the frequency. 3 times 10 to the power of 8 meters per second divided by the frequency in hertz, which is also seconds to the -1. In the final part of the question, again, we've got another wavelength. We need to convert this to a frequency. In this case, the wavelength is given in nanometers. To convert between meters and nanometers, we have to multiply by this factor. This gives us a value of 4.73 times 10 to the -7 meters. Question's asking us to determine the frequency. Plug it into the rearranged wave equation. Speed of light divided by the wavelength, and you should get an answer which looks something like this. As you can see, some of these frequencies are actually very large numbers. That's the end of the first How to